I talked about equilibrium, the circumstance that exists when the net force is equal to zero. When all of the forces add up to zero, there's no influence to change the motion. There's nothing to cause acceleration when the net force is zero. But at the very end of that discussion, I said if you added a little bit of force this way or that, it would throw the system out of equilibrium, and I was interested to know if I could figure out how much acceleration I get. I want to be able to look at a physical situation and work out how much acceleration I should expect. And that is exactly the purpose of Newton's second law. There are, of course, three. Newton's second law, sometimes referred to as the law of acceleration, although I don't find myself saying that, relates acceleration and force. It gives me that answer that I'm looking for. If I can work out the force, then I can calculate the acceleration. The acceleration produced by a net force on an object is directly proportional to the net force and is in the same direction as the force, inversely proportional to the mass. Words. Well, what we've already encountered in this course is that I usually take all of these words and replace them with a mathematical expression that says everything that I want it to say. Here is Newton's second law written in the form of an equation. It is one of the most famous scientific equations and most recognized in the history of human science. Maybe E equals mc squared is a more well-recognized equation, but F equals ma, as we sometimes casually refer to it, is the essence of Newton's second law. What I want to do here is carefully identify all of the symbols that appear in this equation. You're thankful that it's a very simple equation. I mean, x is equal to x naught plus v0t plus 1 half at squared is a more complicated looking equation. This is quite simple. We know what the capital sigma means. It is the sum of. And the reason why Isaac Newton put that there is that he understood, as I've mentioned before, that in any given situation there could be more than one force that is the cause of the alteration of the motion. So you have to account for everything. Literally, sigma F is saying a thing that is sensible in all aspects of life. If you want to get a good result, you have to account for everything. And if you don't account for everything, then your answer is only approximately true, or your results are only approximately good. The sum of the forces. Now I'll remind you that force is a vector quantity. It's not just a magnitude, but also a direction. And we talked about if you have forces to the right, then they all add up the way you'd expect. But if you have forces to the left and forces to the right, they are in opposite directions, and they might very well subtract, as vectors do. Vectors are magnitude and direction, and you have to respect it. Here on the right-hand side of my equation, very simple. The mass in kilograms, which is the measure of an object's inertia, multiplied by its acceleration. Newton's second law gives me a way that if I can understand the forces, I can figure out what the acceleration is. But I could use it in a couple of different ways by doing a little bit of algebra. Sure, sigma F equals ma, but if I divide sigma F by m, here algebraically the m then appears in the denominator, and I've found the acceleration. Acceleration is the net force divided by the mass. By the way, on the last slide, all of those words, and it said inversely proportional to the mass. What those math words mean is that when I rearrange the equation this way, the mass appears in the denominator. That's what that means. Fancy math speak for a simple idea. I could do some extra math on top of that and solve for the mass so that the mass is the net force divided by the acceleration. That hardly ever happens. I'm not usually looking for the mass because if I'm going to go into a laboratory and do some experiments, it's very likely that I have a pan balance there, and I'll measure the mass of whatever I would like to know the mass of. But these equations tell me a little bit about how the relationship between force and acceleration works. For example, If I double the force acting on an object, the acceleration will be doubled. If I look at this equation, F equals ma, and I put a factor of 2 here on the left-hand side, that doubles the right-hand side. And since the mass is the mass is the mass, that gives me twice the acceleration. Don't think about that too deeply. Twice the push gives twice the acceleration. That's very, very simple reasoning. But also, if you double the mass, you get half the acceleration. The reason why is here in the second equation, that if the mass here is doubled, that's a factor of 2 in the denominator. That's 1/2 the acceleration. Don't think too deeply about that. If a thing is more massive, it resists acceleration, and so its acceleration will be less. If I double the mass, then the acceleration will be less by half. Remember that all of our equations of physics represent the physical reality of our universe. Let your intuition guide you as to how it should go, increase, decrease, and by what factor. The algebraic expressions are true, but they're also common sense. But for that to work for you, you have to invite that common sense into your thinking. So here's an example of a calculation with numbers. I find it's true all the time that my students want to see numbers. I love just the equations. I could do my whole thing just considering the relationships among the symbols that represent the physical quantities. But here, imagine that I have, it's very uninventive, I've got a 2 kilogram box, and I see that there are 10 newtons of force directed to the right and 4 newtons of force directed to the left. Well, I want to work out what will the acceleration be. Notice these forces are not in equilibrium. The net force is not 0. Just by inspection, without doing any arithmetic, try not to subtract, there is more force to the right than there is to the left. These are not forces in equilibrium. So this thing is going to accelerate. I want to know how much. So I use Newton's second law for that. The net force is equal to the mass times the acceleration, and I want the acceleration. So if I feel like it, I could plug the numbers in right away. But here, a little algebraic jiggery-pokery, solving for A is the net force divided by M. Well, the net force is not 10 plus 4 is 14 newtons. That's not the net force, because force is a vector and I have to appreciate the direction. They point in opposite directions. So the net force is 10 newtons minus 4 newtons is 6 newtons. Then divided by the mass, which is 2 kilograms, and the acceleration works out to 3 meters per second squared. Very simple and straightforward, but like all of our physics, and I know that I've mentioned this before, you have to put a bit of thinking in when you apply these equations. Almost never do you have the luxury of just taking the numbers and plugging them in and getting an answer. It'll feel like that sometimes, but you always need to be putting thought into what it is that you're calculating. And here, I got what I wanted. I said I wanted to know how much acceleration do I get if this is the situation. And I found that it's 3 meters per second squared. Oh, here's Slim. I guess he's skydiving or something. He's falling. There's Slim. He's jumped off from a high place. Hopefully he is falling to a safe place, like some water or a foam pit or something. But there he is, and he's falling. Slim has a mass of 60 kilograms, and as I mentioned in our last discussion, 60 kilograms is not his weight. 60 kilograms is his mass. Mass and weight are not the same thing. His weight is the force of gravity acting on him. I like to call it F sub g. You could call it W if you want, but we're much better off F sub g, force of gravity. I've got an equation for that. The weight of a thing is its mass, in Slim's case, 60 kilograms, multiplied by the acceleration, which is 9.8 meters per second squared, but you don't mind if I use 10. 60 kilograms times 10, obviously 600 newtons. His mass is 60 kilograms. His weight is 600 newtons. Well, he is falling under the influence of gravity. And I'm going to ask the question, what is his acceleration? Even though I already know the answer. His acceleration is the net force that acts on him. There's only one force. There's only one force acting on him because he is falling freely. My definition of free fall is falling when there's only gravity. My definition of free fall is falling when only gravity is acting. Well, if the net force on him is just that one force, then it's just 600. I don't have to add or subtract anything. 600 newtons divided by 60 kilograms is equal to 10 meters per second squared. The acceleration due to gravity. That's a rather simple and obvious result. The reason why gravitational acceleration happens is because the force of gravity divided by the mass is equal to that acceleration. Now, if you're on a different planet, if you're on the moon or Mars, then the acceleration due to gravity is different. And so your weight is different, and your acceleration is different. It is a very common question of physics about objects falling under the influence of gravity, hitting the ground at the same time, despite the fact that they have different masses. I've already alluded to this because Galileo went to the top of the Leaning Tower of Pisa and took two masses that were different, and he dropped them and discovered that despite the fact they had different masses, and so therefore different weights, they hit the ground at the same time. He would also have discovered, by the way, if he could measure it, that they hit the ground with the same velocity. But one is heavier than the other. How can this be? Well, here I have a brick that has a mass m, and when it falls, the force on it, which is its weight, divided by its mass, works out to be the acceleration due to gravity, like it just did for Slim in the previous example. If I double the mass of the brick, so I put two bricks together here, so double the mass of a brick, then I've doubled the weight, but I've also doubled the mass. And so these fractions, 2 over 2, that's of course 1, and it works out to g. So Galileo's experiment, dropping things from the top of the Leaning Tower of Pisa, now makes obvious sense. Everything falls in free fall at the same rate, no matter what, the mass. But of course, there is such a thing as non-free fall. And in fact, in order to actually do free fall, I need there to be no atmosphere, no air, because the force of air resistance exists. Imagine that I have a thing like a tennis ball that is falling under the influence of gravity. Certainly, it has a weight acting downward. So I have a big arrow that says mg, the weight that causes it to accelerate downward. But the air through which it falls exerts a resistive force known as the drag. So I'm just going to call it D. D is a force, the drag force. And it's subtle, but I wonder if you notice in my diagram, I've drawn the D vector a little shorter than the weight vector. These forces aren't in equilibrium. They don't add up to 0. There's more force downward than there is upward. And so you accelerate downward. But the drag subtracts away some of that force. If I choose downward to be the positive direction, then the drag is negative force. So the net force is going to be equal to, because we know we'll calculate the acceleration as the net force, sigma f, divided by the mass. The net force will be the force of gravity downward, which is just the mass times g, minus the drag force divided by the mass. Well, an interesting thing happens. As you fall under the influence of gravity, not freely because there's air drag, the faster you go, the greater the air drag is. You already know this, everybody does. Because as I walk around the room, I only slightly feel the air because I'm going slowly. But if I ride my bicycle, I begin to feel the air because I'm going faster. When I stick my hand out the car window, I can really feel the air because the car is traveling very fast. The faster you go, the larger the drag is. And the drag gets bigger and bigger and bigger until the net force here in the numerator becomes 0. When that happens, the acceleration is 0 and you fall at constant speed. The constant speed that you fall when the viscous drag upward is equal to the weight downward is called the terminal speed. Not because this is the speed that you're going to die when you hit the ground, but because the acceleration gets smaller and smaller and smaller and smaller until it's eventually zero. The terminal speed is the speed at which you begin to fall constantly. Non-free fall motion. So now, using Newton's second law, if I'm clever enough to figure out what sigma f is, which, by the way, turns out to be the whole problem, if I'm clever enough to figure out what sigma f is, what the net force is, then I can predict how much acceleration I should expect in any given physical situation.